Hi. Matthias is a PhD student at the ETH Zurich. And I Control Your Code is a talk about attack vectors and how they can be mitigated using dynamic instrumentation. Without further ado, Matthias Paya.
Thank you very much for the introduction. Thank you very much for the introduction. I'm going to talk about different attack vectors and how these attack vectors can be seen through the eyes of software-based fault isolation. The motivation of this talk is that current exploits are so powerful because all the applications that we run on a current software system run on a very coarse-grained user privilege level. As soon as you have an exploit in an application, you've got full control of all the capabilities of that software application. And you can also use local privilege escalation to escalate your privileges through auxiliary attacks to gain full root privileges. So the problem is that, still there? Yeah. So, local privilege escalation through auxiliary attacks. So what we would like is a tight security model that limits privileges on both a per application level and a per user level, so that we have different security privileges for each application and for each user level, so that we can limit an application in what it can access and all the different data it can modify, and also on a per user level, so that we can specify that this user is only able to access these files or these services and all that. So the idea is that each application only has access to the data it actually needs, and that is owned by that specific user and useful for the application. So for example, if we have a web browser, we would limit that web browser to internet access and to its local cache. But the web browser should not have access to the data files or to the Word files of the local user, or only if the user wants to use these files to upload them somewhere or to do some other stuff with that data. The talk looks as follows. That's the outline. First, I'm going to introduce the surroundings of the talk. I will talk about protections through virtualization, how we can solve the protection problem or the security problem by adding an additional security layer. And then I will discuss different attack vectors. That's the interesting part for you guys. First, I will talk about code injection, return-oriented programming, format string attacks, arithmetic overflows, data attacks, and mixing different form of machine code, especially x86-64 versus i386 machine code. In the end, I will do a short demo and conclude. So, as you all know, software security is a very challenging problem. We have both managed and unmanaged languages. Managed languages like C# and Java run in a virtual machine, but they are still prone to attacks. We can exploit the just-in-time compiler. We can exploit the libraries these virtual machines or type-safe language use. And there are a lot of different forms of attacks that can still be carried out, even if we run in a managed environment. On the other hand, if we run in an unmanaged environment, like if we have a program compiled from C or C++ source code, we have many more different attack vectors and possibilities. There are buffer overruns, there are missing checks, and all that. So there are many different forms of attacks that exist. And the problem is that all these low-level bugs are omnipresent. And if we have a managed high-level language, this high-level language with all the nice type-safe features and safety guarantees and all that, it still compiles down to low-level code. And this low-level code can be faulty, and we can then use these faults to escalate our privileges. Another thing that is very hard is to eliminate bugs. If we find a bug, it's really hard to get rid of it without breaking the system or introducing new and other bugs. So it's really hard to fix and find them. And programmers currently rely on way too many assumptions. And they're not really sure if it's semantic of the language, a programming language, or if it's part of the operating system or the memory layout or whatever. So programmers assume that their thing that they are using all follows the nice guidelines and all that. But programmers might rely, when they're writing C code, on the memory layout of the target architecture. So they are not sure what the difference between little or big endian is, or different type sizes. If we go from i386 to x86-64 machine code, we have different type sizes. So a programmer might assume in i386 code that a long is always 4-byte long, a long data type. But if we move to x86-64, it suddenly is 8-byte long. And we also have different pointer sizes, variable placement can change, or even your variables in a struct, in a C struct, can change the order. It's not guaranteed in the C language that the order you specify in a C file is what the compiler will lay out. So the goal of this talk is that you will understand the different attack vectors and the constraints, and so that you know how to defend yourself against the attacks. I will show different techniques and security measurements and how you can use binary translation for security analysis. And it's always good to know your assumptions. This talk tries to fit the gap between people that are new to the area of security research. So I will describe all the local attacks, but I'll also try to focus on more experienced people. That's why whenever you see this nice diamond shape on the top right corner, I will go into more detail and really low-level code. If you're a beginner, it's not really important that you follow all this information closely, but if you are a security researcher or interested in virtualization, that's where you have to listen. So the first tool that I'm showing you is protection through virtualization. Like many other problems in computer systems, security can be increased through an additional layer of protection, of indirection. We just add an additional layer on top of all the other layers that we already have. All of you guys will know virtualization on a system level, like VMware or Zen or all the other things, or simulators like QEMU and all that stuff. But we propose a different approach. We use user space virtualization and not system-based virtualization. We use, or we take an application and wrap that application into an additional layer of indirection. And we add a guard between the application and the operating system so that we can control all the machine code that is executed inside that application. And we can also control the borders between the application and the operating system so that we can specify which system calls are allowed and which are not. So if we go from the left-hand side of an uncontrolled application to the right side, we add all these virtualization and security guarantees. We have different security principles that we use. There are two basic principles. The first of them is that all code that is executed inside the virtual machine is translated before it is executed. We add, during this translation process, we add additional security guards. We verify every single machine code instruction and guarantee that it is never ever able to execute malicious code. All control flow transfers to illegal code are checked and verified that they are not possible. So we remove the risk of code injection. All illegal control flow transfers, like ARC attacks or return-oriented programmings, are also checked by adding additional security checks for return instructions. We also catch jumps into other instructions. So if you try to hide your malicious content in other instructions, we catch these by adding a verification toolchain so that we can verify from the beginning of every exported function that every single machine code instruction is valid and reachable. And we also catch switches between i386 code and x86-64 code. That's the first security principle. Using that first principle, we guarantee that every machine code instruction that will be executed in the context of the target application will have been translated first. So we can guarantee that there is no untranslated and unchecked code. On top of that first security principle, we add a second security principle. All system calls that are executed by the application must be authorized by a policy. This policy is used to catch local privilege escalation or to catch unintended system calls, so that if there are data bugs or other bugs in the application, we can still guarantee that the application will conform to the predefined policy that we added during that execution process. We will catch privilege escalation in all the data bugs that execute these unintended system calls. So virtualization in a nutshell looks a little bit like this. By the way, this is the first time that we switch into the expert mode. On one side, we've got the original code, which may contain bugs, which may have been tainted, which may have been evil. The picture shows a couple of basic blocks that form a loop and the exit of a loop. And we also see on the top right corner of this box that the first thing that the virtualization system does is to remove the executable bit of all the executable code of the original application. So if we lose control or if there's a bug in the binary translator and the code jumps back into the original code, it will raise a fault and stop the program. So what we also have to say is that the application never knows that it's being translated. This fact is hidden from the application. The application always runs under the assumption that it's running in untranslated mode. And the virtualization system keeps up the illusion that it's running in an unmodified environment. So whenever we execute a basic block of the application, we invoke the translator first. The translator reads that basic block of the application and translates that block. It verifies the source of the machine code instructions, the individual machine code instructions, the protection level of these machine codes, and also checks branch targets and origins. It does some additional optimization, concatenates a couple of basic blocks, does some inlining and all that. But the most important thing is, security-wise, that we add all the additional security guards on that level. If we have translated one of these blocks, we put that block into our local code cache. The code cache contains translated blocks with the security guards. So on the top right corner, you see that this code is marked readable and executable. So the application runs actually in the code cache, but thinks that it's running in the original code location. So we have to keep up that illusion and translate it accordingly. Whenever there's an indirect control flow transfer, for example, an indirect jump or an indirect call, we have to look in the mapping table. So there's a lookup which maps machine code locations of the original code to machine code locations of the translated code so that we can transfer control back and forth accordingly. So the additional security guards that we add during the translation process are as follows. First, we check the code location. In every exported module or object that the application has, we verify the permissions of the page. And that's done on the object level. So even on a sub-page level, we are able to verify that that code can be executed, or this is a data region, and we may not execute code in that area, or this is read-only or read-writeable or whatever. So we verify permissions on a sub-page level according to the module exported in the file. We also check the targets of the static control flow transfers. So whenever there's a control flow transfer, for example, a call, we verify that we actually target a valid call instruction so that we can switch and check that the call instruction is valid and workable. This check verifies that we are not able to call some other newly injected code to change the stack or do some other stuff. We also add additional permission checks, for example, through the global offset table for all these intramodule transfers. If we have a jump instruction into the middle of an object, we verify that the machine code that we target is actually valid. So if we scan a function from top to that actual machine code instruction and verify that it all sums up. If there's a jump into another module or into another function, we forbid that because there shouldn't be any intramodule transfers using indirect jumps or other jumps. So these are the static security guards. They can be added for all the static control flow transfers. But we also have dynamic control flow transfers. That's where the dynamic security guards come in. So we have to add dynamic security checks for all these dynamic control flow transfers. These are, for example, return instruction from a function, indirect calls, and indirect jumps. We have to verify, whenever we execute such an indirect control flow transfer, that the target is valid and translated. Untranslated target, or if the target is untranslated, we have to fall back into the static check and we have to invoke the translator as well. So we also add these dynamic checks that are executed whenever we execute an indirect control flow transfers. The static guards are only invoked during the translation and the compilation of the machine code. Then we can run the optimized code without any additional checks. But if we have indirect control flow transfers, we have to execute these checks whenever we execute the code again. And for example, to verify the return instructions, we build a shadow stack with translated and untranslated addresses. So whenever we pop a function frame from the stack, we verify that the return instruction has been there before, and we also have a verified translation target that we can then use to jump back to. So the second principle, the second security principle, the system call authorization that I explained to you before, redirects all system calls to a policy-based authorization framework. First of all, for the broad majority of system calls, we've got a policy that specifies on a per system call basis what arguments are allowed or not allowed and how we can map these arguments and all that. But we also add an additional authorization function for these redirected system calls. So for a couple of system calls, we have to implement additional code in user space. So if we have the mmap system call, for example, we have to verify that the application code does not map anything into the code of the binary translator or the virtualization system. For mprotect as well, we have to verify that the application is not able to mark other code as executable that could hide from the binary translator. And we also have to check the fork system calls. Whenever we start a new process, we have to verify that the new process is started under the control of the binary translator as well. And also the same goes for clone. If we suddenly have a rogue thread that trashes our data, we have to verify that this cloned or new thread runs under the control of the binary translator as well. All the system calls are either allowed, redirected to the authorization function that does the additional checks, or the program is terminated with a security exception. So that was the rough introduction into the choice of virtualization systems. I will now talk about the different attack vectors that you will be most interested in. So all the attack vectors that we will discuss today redirect control flow in one way or another. New or alternate locations of code are reached that would not be executed in an unaltered run. So we either inject new code, we alter the control flow to new code, or we do some other fancy computation that changes the program in one way or another. Every attack exploits the fact that the programmer or the runtime system was unable to check specific facts and specific factors. These facts can be the bounds of a buffer, type overflows, type underflows, or any out-of-bound memory access or memory write. The first of the attack vectors is code injection. Code injection injects new executable code into the process image of a running process. So code injection can either be carried out into a buffer on the stack or into heap-based data structures. The second level of the attack is a redirection of the control flow to that newly injected code, maybe with an additional knob slide or whatever. This can be carried out either by overwriting the return instruction pointer, so that when the function returns, we fall back to the injected code, or we can also overwrite function pointers, destructors, or data structures of the memory allocator, but more on that later on. The first form of code injection, stack-based code injection, exploits a missing or incomplete bound check on stack-based buffers. The exploit itself is twofold. First of all, we have to find a buffer, fill that buffer with new machine code, add maybe a knob slide, verify, or know where on the stack that buffer is, and we then grow that buffer downwards and override the return instruction pointer so that the return instruction pointer points back into our buffer. Whenever the function returns, it will then execute our malicious code. Constraints for this exploit are an executable stack, like i386 has it, missing and faulty bound checks on a stack-based buffer, no stack guards that are present, and the return instruction pointer must be verified or checked. Must not be verified or checked. There's a nice paper by Aleph1 which explains that in great detail. So if we have some vulnerable code here, we see that we've got our nice function foobar and a string that's passed as a first parameter, and we've got a local array called TMP with a maximum length, and we use the nice string copy function to copy the string argument into our temp variable, and we then compare the temp variable with a pre-initialized value called foobar. Here we see that there is no bound check in the string copy function, and we can, and this will result in a buffer overflow on the stack. So when we execute that function, the stack looks as follows. First, we have the caller that has the original stack frame on top of the stack. It will then push the first argument onto the stack of the callee. It will push, or it will execute a call instruction which transfers control to that new function. That new function will open up its own stack frame with a safe base pointer, and it will have a local variable called TMP on top of the stack that will be used for the local computation. The string copy function then takes the length of the user input and copies that input from top of the stack downwards into the temp array. So it looks as follows. If we do a malicious call, we first overwrite or add our exploit and knob slide into that buffer. We then overwrite the base pointer with some values that we don't care about, and we overwrite the return address so that it points back to the top of the buffer. As soon as we return from that function, we will not return to the caller, but return into the exploit and knob slide, and will then be able to execute the malicious code. The second form of code injection is heap-based code injection. This exploits a missing or incomplete bound check on heap-based buffer, and is actually very similar to stack-based overflows. This exploit also uses two steps. The buffer on the heap is filled with machine code first, but then we also have to overwrite the function pointer in that struct, a vtable entry if we have an object-oriented language like C++, and when we redirect that vtable entry, we will be able to redirect the control flow as well. We have to override a glibc destructor or also some memory alignment data structure or memory management data structure to redirect the control flow as well. The constraints that we have are an executable heap, missing and faulty or faulty bound checks, and a successful redirection of the control flow. So the exploitable code looks as follows. We first have a nice struct with a local buffer with a maximum length and a function pointer that takes 2 arguments and compares these arguments. And our function is foobar heap, takes a pointer to one of these structs, and a string argument copies that string argument into the buffer and then executes the function pointer. Once again, we have no bound check when the data is copied. And these bugs are actually still really common. So the struct looks as follows. We have the buffer and we have the compare function pointer. The user data is copied from top to bottom. And if we execute it in malicious context, we first override the buffer with our exploit and a nice little knob slide, and we will then override the function pointer so that it points back into our exploit code or somewhere into the knob slide. So what would a binary translator do when he sees such control flow transfers? First of all, the binary translator would stop the program when the control flow transfer is detected first, before the shell code is even translated or the knob slide. And there would be 2 exceptions. First of all, we have code that is about to be executed that is in a region that is not marked executable in the original object file. And we have a function call or a return control flow transfer to an unexported or unknown symbol that's either on a heap or on a stack. And we have a mismatch for our shadow stack and all that. That's exactly the point where we could stop the execution in the virtualization system and stop the program and contain the security of the system. For an analysis-based system, we could stop the exploit, we could analyze the shell code that has been injected into that buffer at that point, because we know exactly when we would lose the control over the program. That's exactly where we can break, attach a debugger, and then analyze all the machine code that has been added into the image of the application. That's how we can catch new exploits in all these security holes. We have all the information on the stack where the different data structures lay, and we can also dump that information into a file. So we can use the binary translation and virtualization toolkits to audit the software and to test the exploits. Another form that is more complex, but also based on some form of overflow, is return-oriented programming. This exploits already existing code sequences and does not rely on the fact that we have to add our own machine code into the process image. So we have to prepare the stack so that it looks like as if we would return to different functions with different parameters. So we actually force the program to change the stack so that we can give the illusion that we execute different function tails one after another, thereby executing arbitrary code. A stack-based overflow is used to prepare multiple stack invocation frames that are popped one after another. There are also functions that rewind the stack and add new frames and all that. The control flow is redirected to function tails, mostly of libc functions, and there's a complete library available that enables you to execute arbitrary code using stack invocation frames only. Constraints for return-oriented programming are a missing bound check for the initial stack-based overflow, and the return instruction pointer must not be checked, and we must be able to redirect control flow to these new locations. So once again, this is the same code as we had with the stack-based overflow. We have a missing bound check for the string copy, but this time we don't inject our own code, but we add additional stack frames that invoke new functionalities. So once again, the caller initializes the stack frame, pushes the first argument to the function, calls the other function, which then in turn opens up its own stack frame, adds its buffer, and then uses the string copy function to copy data into the temporary variable on the stack. So if we exploit this for a return-oriented, if we use return-oriented programming to exploit this bug, we don't care with what we override the temporary variable. But if we only use one stack frame, we also don't care what the saved base pointer is, because we only use one function call. We override the return address with a pointer to the system function, and we push the base pointer after the system call, which will then be our next pointer. That's what we can use to rewind the stack, for example. And we will also add a pointer to the first argument of the system call, which will then execute a shell for us. So what would the binary translator do? This time, we don't have any new code that is injected into the image of the running application, but the binary translator or the virtualization system would stop the program when the control flow transfer to the system function is detected, before the function tail or the libc function is actually translated, because we are able to verify the return addresses on the stack. The exec system call that is executed in the system function would be stopped as well, because it doesn't accord to the policy of that application. A real attack, if you would want to use this attack in a program, would chain multiple libc calls so that you can actually execute arbitrary code. And you can also inject code into the address space, use a return-oriented programming attack to call mprotect, which will in turn make your code executable, transfer control to that executable code, and then, bam, you own the application. So these attacks are all nice and good, but all rely on buffer overflows. The attacks I'm going to discuss now are format string attacks and data attacks. They don't rely on buffer overflows, but use different functionality to exploit the system. Format string attack exploits the parsing functionality of the printf family. If a user-controlled string is passed to the printf function, we can do some nice additional things with that, especially if we are able to control that string. By %n, we can actually use random writes to memory if we prepare the input string carefully. So a nice combination of %x and %n can be used to write anywhere into memory and to do to raise havoc and redirect control flow wherever you like. The constraint for this attack is that the format string must be allowed to contain %n and some printable character to write to memory. And it can be used for random writes. For example, we can override the return instruction pointer, destructors, vtable, inject code, and we can also combine it with different attacks to prepare and launch other attacks as well. So you will all know printf. Printf is a nice way to debug, to print values, to print strings and all that, addresses. But there are also some less known and interesting printf features. Using, for example, we can just print the enhanced parameter. So we have out of order access in the parameter sequence that we can add. And we don't rely on a specific number of parameters as well. And we can also use a special format to print the character or to print the parameter using m bytes. We can also print the nth parameter using m bytes as well. And the interesting feature that this attack relies on is to be able to write half words to memory. So using %hn, we write the amount of printed characters to the given parameter, to that pointer. And we can combine these features to get random writes to memory. So if we have our vulnerable function. Once again, we've got a local buffer, we've got a string copy, and we then use printf. This function also has a buffer overflow, but this time we are not interested in the buffer overflow here. So we can use references to our string to retrieve pointers, first of all, so that we can specify random writes to memory to predefined addresses that we injected into that string. So if we pass 2 addresses as a part of the string and construct the string in a nice way, we are able to use 2 half-word writes to memory to redirect control flow in a nice way. So the string looks as follows. The effect of the string above is that we write 2 half-words, 2 times 2 bytes, to the 2 addresses that are specified in the beginning. The first 8 bytes of this string contain the 2 pointers to the half-words, and the next part prints n bytes, increases the number of printed bytes actually, and we then write the number of already printed bytes to the first parameter. We print some more bytes, and we print the number of already printed characters in total to the second address, which then redirects, in this case, the return instruction pointer to some other function that wouldn't be called in this case, in the normal case. The binary translator, or the virtualization system, is not able to detect the random write to memory. It would be way too expensive to check every single memory write. But it detects the change of the return instruction pointer to the new function and is able to catch that as well. And the system call guard also checks the arguments of the system call, so it will be able to stop the program in that area. And all the policy violations will be detected, and the program is stopped and can be analyzed at that point in time. Random writes to memory are only detectable with full memory tracking. The virtualization system that we have now comes with an overhead of 6 to 8%. If you use full memory tracking, we have an overhead of like 1,000 or even more, which is not really tolerable for a real-world application. But we are able to detect the change of the control flow whenever we would follow it. The next exploit is an arithmetic overflow. These exploits are still really common and really hard to find. And they exploit overflows in data types. Sometimes the bounds are checked before an arithmetic operation. So you do a length check before you do a multiplication or a shift or whatever. And the problem is that data types are all of a specific length. And arithmetic operations can cause overflows, underflows, and most of the times unchecked or dangerous values are passed to functions that depend on user input. Constraints for this attack are lax or implicit type conversions, sign errors, rounding errors, type overflows, and all these nice things. If we have an attack like this code was found in OpenSSH, and kind of an old version, but still really interesting to see. The number, there was a number that was parsed from a packet, from a user-controlled packet, and if that number was bigger than 0, we used a malloc, allocated some data, and then copied data from that packet into our response. Well, this code looks correct on first look, but if we look more closely, or if we pass dangerous parameters that into the number NRESP value, we can cause an overflow. Size of int is 4, and if we pass 40 millions in hex as this parameter, it will then be multiplied by 4, which will result in a type overflow and wrap over to 0. So xmalloc succeeds and allocates 0 bytes. But the following for loop will trash our main memory with weird stuff that's in that data and override other data structures, which enables us to gain control of the application. And these bugs are really common because you wouldn't think about these type overflows in that regard. So these arithmetic overflows are often used to overwrite some part of the memory and prepare a secondary attack, like a secondary buffer overflow or return-oriented programming or things like that. It can also be used to inject code similar to a buffer overflow because we have some random writes. The virtualization system detects the control flow transfer to illegal code, and the system call authorization stops and protects the system from these form of attacks. So as a food for thought, while we are translating all the machine code, we could also add additional guards and checks to analyze these flags registers and could use these to track overflows and maybe prohibit different alloc functions or whatever if we detect such a problem. The last attack I'm going to discuss is a data attack. Exploits a missing or faulty bound check and writes data to an user-controlled address. And it's almost as much fun as format string exploits because we have a random write to memory, which we can use to initialize some data structure to redirect control flow or to do some other malicious stuff. So the position and the value of these functions are often only partially checked. Maybe if there's an integer overflow or if we combine it with some other attack, it will result in a random write to memory. This looks about like this. We've got the code, data, the data array at the position pos will be written with the value. In machine code, it looks a little bit like this. We load the pos argument, we multiply it by 4 using a shift. We then construct our pointer. We write the value into a register and then write that register to memory. What limits us to use negative values for that value? So we actually have an indirect write to somewhere to memory, which can then be used to override other data structures, vtables, or other nice pointers. And in turn, we will be able to get control of the system. So we have a random 4-byte write to memory relative to the position of the data array, which is often static if it's a static array in an exported symbol or something like that. So we can easily control that. The only constraint that we have is that pos and value are user controlled. These things are hard to detect, but the binary translator stops the illegal control flow transfers to these illegal system calls. We don't detect the write because that's perfect legal code, but we detect whenever the exploit triggers and would execute the injector code. Total. So a fairly new thing that's coming up is mixing x86-64 and i3-86 code. Modern kernels, all of your 64-bit operating systems will support both x86-64 code and i3-86 code in parallel. In a malicious program, you can even mix x86-64 and i3-86 code and switch between one format and the other all the time. This was not intended, but is possible using a combination of long jumps and some other auxiliary things so that you can just make it easier for the loader to work with both binary formats. All the system call authorization tools that are around and all the static verifiers work on the assumption that only one form of machine code is used. Even ptrace had that bug that it was not able to detect a switch from x86-64 to i3-86. Now the big problem, this wouldn't be a problem if we have the same system calls in 32 and 64-bit mode, but the system calls are actually really different. All the system calls have different numbers and sometimes even different parameters if you switch between 32 and 64-bit mode. Checkers can be tricked to allow dangerous system calls because they assume that you are calling a simple, not dangerous 32-bit system call, but in fact, the same number maps to a dangerous system call in 64-bit, and you can then use this exploit to gain control of the system and escape the system call authorization tool. Only a dynamic security system that is 64-bit aware can guard against these threats, and you have to be able to detect the switch between 64-bit code and 32-bit code. So there's the seccomp sandbox that is to be used in Google Chrome, and it only allows exit, read, write, and sig return system calls. But if we switch between different 32 and 64-bit mode, we actually get access to the stat and chmod system calls and can do some weird stuff with our open files and escalate our privileges. This is just a nice example of that problem. The binary translator detects the long jump that switches between these two modes and is able to switch the system call tables accordingly and use the newly specified table for the correct layout. So these were all the exploits that we discussed. I now have prepared 3 exploits, and we do a quick vote, 10 seconds or so. I've got heap-based code injection under the control of the binary translator, return-oriented programming, and a format string attack. Who is in favor of heap-based code injection? Raise your hand. 20. Who wants to see return-oriented programming? About 80. Who wants to see the format string attack? Okay, I think return-oriented programming won, so we'll do that one. So we first have a look at our code. It looks as follows. We've got this nice function. It prints some arguments so that we don't have to care about all the locations and all that. And it uses sprintf to print some stuff into a buffer. And then is called by the main function. The main function is here, actually calls that nice function up there, and that's where the exploit will happen. So that you actually see something, the thing we do is we override the stack with a call to system, and we pass a parameter to the shell variable. The shell variable is always there. It will drop us into shell. We specify bin sh as our default shell. We use ps1 as a parameter, and we let it run under the control of the binary translator. We execute that program, and first we pass the parameter foobar as only parameter to that program. We execute it, we start the binary translator, we see the output. Shell is at that address, system is at that address, the last argument is at that address. We copied foobar into the buffer and return safely. On the other hand, if we've got the same string in the beginning, but as a parameter, we invoke Perl. We overwrite the buffer, these 8 bytes, with A's. We don't care about them. We've seen that in the, on the slide before. And we use that address. We use coffee as a new base pointer. And this is the call to system. That's 800483B0. That's that address over here that you see. Okay. And this address, if you wonder, that D5E5 is actually the correct part of the shell. We execute it, we start the binary translator. We see that the target shell is at that address. We copied our nicely constructed string into the buffer, and we see, bam, we are dropped into a shell. So now the question is, what actually happened? Let us look at the code that has been executed by the binary translator before we lost control. So we go down. That's all the code that has been executed in a binary translator, and we can analyze it, every single machine code instruction that has been executed in the original program, copied to the code cache, and down here we see the last 2 instructions that have been executed as a move of OXB into the EAX register and a system call. These two calls were the last two calls that have been executed in that application context before we lost control. The binary translator would have stopped it way before that if we added the security guards. But if we use it for security analysis, bam, that's where we lose control. We see the exploit that has been executed, and we are here in a shell and can analyze that further. This can also be used for debugging and all the other nice features that you want to do to test your exploits and bugs. So to wrap it all up, user space, virtualization, and binary translation contain security problems, and security violations are detected and the program can be terminated before any evil code is executed. So user space virtualization is a fine-grained per process, per user trust model, and it adds additional security on that. On the other hand, from an attacker's perspective, we can use virtualization to analyze these threats. We can analyze the malicious payload, we can test the exploits, we can observe the control flow, transfers, locations, and break-ins. The tool I presented here is called FastBT for the binary translator itself. It supports the full IA32 ISA, x86-64 is almost complete. That part will be released in the next couple of days. There's absolutely no kernel modification necessary. You can download it, you can compile it, it comes with test cases, it comes with exploits, you can play around with it, and you can have fun with it. Thank you very much for your attention, and I'm happy to take your questions. Any questions? Yeah?
So here's a question. SE-Linux basically relies on policy for stopping the unapproved kinds of system calls, right?
Linux does rely on?
SE-Linux, right?
Yep.
So we have an intercept after the regular Unix permission check, and there are permission vectors, and it can all be reduced to some type theory. Okay. Now, your policies compared to SE-Linux policies, are they more fine-grained, less fine-grained? And if so, how do you deal with the complexity of writing a policy and debugging a policy? Because SE-Linux policies have not been a fun thing to debug,
yes,
and they do need debugging.
I know. That's actually a very good question. That's why we have a layered approach to these policies. First of all, you can define a simple policy based on policy numbers, arguments, and all that. That's a simple text file, and you can just specify this application is allowed to run these couple of system calls with these arguments. That's still very simple. You can either code it by hand, and we also have a recording application that starts it in demo mode, records all the system calls, and then drops it into a file, and you can manually compact them by generalizing different arguments. That's one thing. But the second thing is, for specific system calls, you want to add additional code which do additional checks, like maybe the call address. So this system call can only be called from this context in this libc function, but may never be called by the application code itself. So the policy itself is more powerful than the SE-Linux policy. But if you want the more powerful features, you will also have to write additional code.
If I may follow up, if no one else knows, I'll wait.
Oh, hello. I want to ask you about how the binary translator is handling with the protected binaries, because the protector often uses the technique of jumping on the whole memory and writing everything. And
you mean self-modifying code? So as you have seen in the on that slide over here, we map the code of the original application is mapped read-only. Whenever the application writes into that area, we will get a protection fault. We will be able to catch that protection fault, remove the read-only protection, add a writable bit, and add a debugger or like a protection after that. So the write happens, we retranslate that code, and we will continue to translate the application.
This is kind of encapsulating the write. So yes, catching the writing to
Yes.
own code, securing this write, and yeah, okay,
Exactly.
thank you.
So the code is always read-only. If the application itself writes to that code, we have to remove that protection bit, get the modified bits, retranslate these bits, and then continue the execution. If we only have protectors that scramble the machine code in somehow, this virtualization system can actually be used to dynamically remove the protection. We have, if we have jump instructions that don't do anything or that just jump around in weird basic blocks, then it has automatic basic block merging and all these things based on the trace of the dynamic execution of the program. So all the static code scrambling is automatically removed as a side effect of the translation. If there's self-modifying code, we have to retranslate different parts of the machine code. But this is not that common for legal applications in a way.
The internet asks, why not use hardware virtualization, i.e. CubeOS, instead of slow and error-prone DBI?
Slow, it's 6 to 8% overhead. I wouldn't really call that slow with all the additional security guards. If you use the hardware virtualization, for one, you also have like 3 to 5% overhead, and you only simulate, or you're only able to virtualize on a very broad level. On the DBI level, I'm able to control every single machine code instruction that is executed. On the hardware virtualization level, I won't be able to get that fine-grained of a control. On the hardware level, I will only be able to catch page faults, switches to ring 0 and all that, or to the operating system. But on the software side here, I will be able to catch every single change in the program itself, and I will also be able to protect the data structures of the application. Hardware virtualization is for the whole picture, to virtualize the whole operating system. This user space virtualization is to virtualize single applications.
Another question is, how does this works in practice on a Windows system?
Well, I'm still doing a PhD. I didn't really make a product out of it yet. It might be coming. There are talks about that, but development on Linux is a lot simpler than development on Windows. I looked into Windows development as well, but there with all the system calls are different, and it's actually a lot harder to keep the control of the application. But if there will be a product in the end, Windows is a must, actually, if you look to the market.
Any more questions?
Okay, thank you very much. I'm still here for questions.
Hello,
Hi.
I have a question about hardened kernels. Are there any attacks which can bypass stack smashing protection and PACS and GRSec, in which you can catch with the binary translation?
In GRSec, well, GCC currently also already has some form of stack protection and all that. But if you use, for example, a format string attack, you can redirect the return instruction pointer to some other location. And this won't be detected by all these stack protection add-ons that are currently available. And I will be able to detect that change of the return instruction pointer because I have a shadow stack that is not visible from the application itself, but is controlled by the binary translator. Did I answer your question?
Yes, but PAX is also able to detect a change in the control flow. So if you want to change the control flow, PAX is able to detect it and kill the program.
So it also uses some form of binary translation? That part?
Maybe, I don't know.
It must. Otherwise you don't have control over the individual control flow instructions. Or the
okay, but you have to modify the kernel for PAX.
Okay.
The internet asks, can BT deal with compiled languages that use a garbage collector?
As I already explained, all the code is mapped as read-only. So if you change the code, it will retranslate it. The garbage collector is actually not that much of a problem because garbage collector only collects the actual data objects. And in many operating or virtual machines, it doesn't collect the code at all. So the application can use memory management like any other application. So the garbage collection would not interfere with the virtualization system at all. Only if you recompile different code regions, we have to retranslate them.
The internet asks, how do you switch between AMD64 and i386 mode? Do you depend on the kernel to provide both code segment types?
It's actually a long jump that switches between these two modes. And it's a special machine code instruction, a special encoding. And as I'm translating every single instruction, I see that this is a long jump, changes the segments and all that, and I can detect that and then switch accordingly.
Any more questions? No?
Okay. Thank you very much. I'm still here around, so if you have questions, come and talk to me.